Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a couple administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, someone will make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will provide an overview of SourceStop, a new technology for the effective treatment of PFAS contaminated soil and groundwater in the source area. With that, I'd like to introduce our presenters for today. We are pleased to have with us Dr. Paul Erickson, Vice President of Research and Development with Regenesis. Paul Erickson oversees the commercialization of new environmental solutions to address complex remediation challenges. During his time with Regenesis, he has led the development of a number of remediation products and technologies, including Petrifix, Aquafix, Flux Tracer, and SourceStop. He earned a bachelor's degree in chemistry from Florida State University, a master's in chemistry from the University of Minnesota, and a PhD in environmental chemistry from ETH Zurich. He is an author on over 20 peer-reviewed scientific publications, mainly in the area of environmental chemistry. We're also pleased to have with us today Steve Barnes, Remediation Services Director at Regenesis. Steve Barnes has over 20 years of experience as an environmental geologist and project manager relating to soil, sediment, and groundwater contamination throughout the US while working under various regulatory agencies. Steve Barnes has a bachelor's degree in geology from Southern Methodist University, as well as an MBA from the University of Notre Dame. His experience includes the evaluation, selection, and implementation of remedial design methods, the design, operation, and maintenance of dual-phase extraction systems, large-scale dig and haul remedial projects, soil and sediment stabilization, and in situ groundwater and soil treatment using chemical oxidation, chemical reduction, enhanced bioremediation, and sorption. Most recently, he's been responsible for managing regional project managers while overseeing the daily operations of the Remediation Services Division. All right, that concludes our introduction. So now I will hand things over to Paul Erickson to get us started.
Thank you, everybody, for joining us today. What we'll talk about today is a new product, really family that we've developed with SourceStop, and how you can use that to treat PFAS in soil and groundwater in source areas. And so with that, we will jump right in. So first, just a quick agenda. So I'll start by doing the normal introduction to PFAS and set up the source plume system that we're oftentimes managing on PFAS impacted sites. And then I'll spend some time going through the new product that we've been working on here at Regenesis, or product group, which is SourceStop. And after that, I'll hand things over to Steve, who will get more into the nuts and bolts of the application approaches and in the field use scenarios that one would use these types of products for, and then get into some of the implementation work that we've done already here at Regenesis. And so let's dive right in on PFAS source zones. And so first, I'll just introduce which PFAS that we're talking about today as a part of remediation of PFAS. And so just look at this PFAS family tree, and you can see that there's, as many of us are familiar with, quite a list of PFAS. And I'll walk through what we're talking about, what we're going to be looking at from a treatment standpoint. And, you know, per and polyfluorinated alkyl substances is a big group, and we can divide it into kind of three big classes: the PFAS polymers, which are not really of environmental concern. So think PTFE, which is Teflon, so things that we're not going to really see moving around in the environment. And then you move into what we do see more commonly in the environment, and that's these either polyfluorinated PFAS or the perfluorinated PFAS. And the polyfluorinated PFAS we'll see these in the environment in the form of precursors, which can then break down into these really environmentally persistent perfluoroalkyl, so really these fully fluorinated species, which can be of shorter or longer chain. The shorter chains are more mobile. We see these move a lot faster through the environment, and the longer chains, which are more persistent and more problematic, and really the target of more regulatory efforts. And broadly, you can classify these perfluorinated PFAS as either sulfonates, so they have a sulfonic acid, or a carboxylate, a carboxylic acid group that terminates them. These are the ones that we're going to be speaking mostly about, just simply because this is the target of most of the regulations that are coming down the pike here shortly. And so for PFAS source zones, the one common culprit for contaminating PFAS source zones was the use of AFFF, so these aqueous film forming foams. And while not the sole source of PFAS in soils, it is a large, use of these foams is a large contributor to a lot of the source zones that we see, especially at airports and fuel depots. And it makes sense. These were products designed to be applied directly to ground surface for the suppression of fuel fires. And especially legacy forms of these products contain significant quantities of PFAS. So in excess of 75 grams per liter of PFAS in some cases. So when diluted at 3 to 6% and sprayed directly to the ground, these were major sources of PFAS that we now manage, and we're working on remediation efforts. So when products like AFFFs and other sources of PFAS get released to the environment, while we are typically worried about managing groundwater, being protective of groundwater, the source of the contamination is oftentimes what's left over in unsaturated zone soils, or the vadose zone. And so after land application, these PFAS are making their way down through the vadose zone. They're driven by recharge from precipitation. So rainfall then comes in, dissolves some of the PFAS, and carries them downward on its way towards the water table. And so if you look and see where do you find most of your PFAS in just a sampling of different sites, which is what this paper here, this Brousseau paper from 2020 looked at, you see that most of your soil mass is up in the upper section, in most cases, of vadose zones, making its way downward with time. More of your long chain, which is in blue, you see them up in the top. It's a bit more even in terms of distribution for your short chains. Makes more sense. They're a little bit more water soluble, more mobile, and so a bit more even in distribution. But they're on their way towards the groundwater, which is what you'll see in terms of, if you look over time, what one would expect. And so this graph here is a concentration profile at a few different time points. So at 10, 30, 50, and 80 years, where would you find most of your PFAS mass in a vadose zone? And you see that over time, your mass is slowly making its way from these source zone soils after you had a release, making its way down towards the water table, where it eventually discharges into the groundwater. And so that's what we see here, is that over time, different areas that are experiencing different rainfall and have different soil types will have mass discharge. So, 0 being none of the source zone mass has made it to the water table, 1 being all the source zone mass has made it to the water table. That'll happen over various time frames depending on your location. So the NJ refers to New Jersey, or different soil types. So AccuSand here being less organic rich than a Venton soil. And so what that means is that if you have a lot of rainfall, you get more of your mass discharge quite rapidly. Whereas if you're somewhere like Arizona, less rainfall, less recharge, that soil mass in the vadose zone stays there longer and discharges over a longer period of time. And so that leaves us with this setup where we've got a source area that's feeding a plume that we're left to remediate. And so let's look at some of the places that you're working with respect to a source area, and that would be these vadose zone soils where you've got high concentrations of PFAS absorbed to the soils. And then within the groundwater, you've got high concentrations being directly beneath that source zone. This is where you find your highest PFAS concentrations. And we'll get a little bit more into both of these zones. And what we won't talk about today much is the management of PFAS in these more dilute down gradient plumes, which is an option that at Regenesis we have solutions for that Steve will touch on a little bit later. And so within the vadose zone, we know that the PFAS that are present and discharging over some rates, they're held onto by the soil matrix in a couple of different ways. One is that these PFAS, they'll bind to naturally occurring organic matter. And so the organic carbon that's present in our soils is one place that the PFAS get pent up and slowly released from. And then within the capillary fringe zone, but also the vadose zone in general, you've got a lot of air-water interface. And we know that these compounds, PFAS, being surfactants, they like to hang out at this air-water interface. And so, these are some of the mechanisms that's holding on to these PFAS that are in these source zones as they're slowly then leaching out and feeding our groundwater plume that can go on for quite some distance. And so let's look at source zone treatment, what some of the needs are in order to remove the risk to our groundwater and really try to manage the plume at the source when appropriate. And so each of these different areas is going to require a different approach for the different issues that you're facing. So within the vadose zone, as we mentioned, you've got a lot of mass, and so you're going to need to have a high amount of sorbent that we place here because we've got a high mass of PFAS present. And as we said, this is what's discharging to the groundwater and driving and sustaining our plume that we have. And so what we want to do is, one form of remediation is immobilization. And I'll talk a little bit more about the approach here. But what we're going to do is we're going to put something into these soils under an immobilization treatment that reduces the leachability of the soils, keeps them in place, and prevents this continued discharge to the groundwater, just drastically slow down or eliminate this process of discharge to the groundwater. Within the saturated zone, your PFAS have already made it, there's benefit to putting more carbon in this area as well. It can be through a few different regions, but the idea is that this capillary fringe where the water table has come up and down, there's an excess of air-water interface. So this is a convenient place to inject, in most cases, additional sorbent to mitigate the migration of our PFAS within this area. And so injection is one option. I'll get into that. But again, the idea is that we're trying to slow down the migration of these PFAS, which are driving your plume development. And so again, more sorbent can be added to this area as well. And the end result then is stabilization of your mass in these areas. And so a bit more from an academic standpoint on the approach, immobilization versus either removing your PFAS or thermally destroying it, some of these other technologies that are less well established can be much more costly. Immobilization is an approach that has been rather well studied and is cost effective in many different areas. And of the sorbents that are available to us, activated carbon amendments have been used for quite some time, and there's a good body of work that shows that they can be effective over the long term. So I'll point to this one publication that came out in 2023 that looked at the long-term effectiveness of carbon-based amendments in soils for PFAS immobilization. And so the study, if you're interested, you can find it here. Here's the reference. This particular study looked over a series of 4 years, so they can be effective for much longer than this, but this is some of the most long-term data that's out there that's been published. And looking at your different options here, so T being untreated here, biochars being the B one, which is another carbaceous amendment, and then activated carbon B and C, you can see that, especially versus no treatment at all, using activated carbon-based amendments can really provide significant leachability reduction on PFAS impacted soils. So that's the science behind what we're hoping to achieve when we use products like SourceStop. And so I'll go through what the different products are that we've developed and talk about some of the attributes and when we want to use one versus the other. So SourceStop is available as these two different formulations, one being a liquid and one being a solid. And that gives us some flexibility and adaptability in terms of when we use the amendments. And I'll get into what the benefits of each are here in a moment. But again, we're using sorbents to immobilize our PFAS in the different places that we may find them. And it gives us some flexibility that when we get to the field, Steve will really get into. And both use colloidal activated carbon, which is something at Regenesis that we've had in different product forms for some time. And I'll talk about the benefits of that now. So colloidal activated carbon is activated carbon, but we bring it down dramatically in size. So it's 1 to 2 microns in diameter, our average particles. This allows better distribution, so you get penetration into soil clots if you're talking about soil mixing better. And if you're talking about the liquid form, it gives you better injectability. So you can see here an image that shows you that these particles can coat soils, so you get good attachment of your small particle carbon onto soil particles, and that's what this image is showing here. But some of the other benefits that we'll get into of using small particle activated carbon is this faster kinetics. So I'll show some lab-based demonstrations that really drive home that point in a moment. But you get a strong adsorption with activated carbon, and then you get kinetic benefits when you move to such a small particle size. And you also get better distribution benefits, again, because of the particle size. And so for the liquid form of SourceStop, it's a black ink-like product, and really the intent is more for injection based. It can also be spray applied. And when the project calls for targeting these particular areas that you can reach by injection, within the saturated zone primarily, this is the product that you would go for. And we've had SourceStop liquid form has been available for a little bit longer. So what I'll spend more time on talking about today is the solid form of SourceStop that we have now. And what it is an engineered conglomerate. So it's a blend of both colloidal activated carbon as well as powdered activated carbon. And both have benefit. When we're working in these highly contaminated soils, we're going to need an overall high loading of absorbent. And so that's what a product like this provides, is you get the benefits of colloidal activated carbon, and then also the ability to use the total sorbent loading that you need to fully immobilize, really drastically reduce the leachability of PFAS on impacted vadose-owned, source-owned soils. So SourceStop as a product is designed to minimize dust. So again, it's this conglomerate of both powdered activated carbon, which is very messy and dusty, and you don't have that same problem with this product. You also have that colloidal carbon that isn't dusty in this formulation that we've developed here. And so you don't need dust suppression if you're using a product like this on site. And so that's in stark contrast to something like a powdered activated carbon, which if you've ever worked with it in the field, it's quite messy. It's dusty, it gets all over the place. And so that's what you can really see here in this photo, is that if you take an excavator and mix around powdered activated carbon, you'll get this big dust cloud. But using something like SourceStop, one of the key intents was to develop something that would give you those same benefits plus deliver colloidal activated carbon, but isn't dusty. And so you can see us pouring some out of an excavator bucket here. And in contrast to that powdered activated carbon, very minimal dust and no need for suppression. And we're quite excited about this delivery mechanism. So again, the objective is leachability reduction. So we're mixing in our sorbents, and with something like SourceStop, you're delivering a powdered colloidal carbon that we're mixing in. It looks like a granular carbon, but it disintegrates when you mix it into your soils. And so we've got good distribution is what you need when you're trying to treat vadose-owned soils. You need to get this material well distributed. So, and that's because you want your PFAS to really repartition, come off of your soils and go onto your added sorbent so that you minimize, near eliminate leaching is the objective with a treatment approach like this. And so to highlight kind of what the look of this material is versus how it performs in the field, you can see here these beakers where we used either granular carbon of similar size to what we would deliver SourceStop at, and then also SourceStop. And for each of these beakers, we mixed in about 1% of either the granulated carbon or SourceStop solids, added a little bit of water, and then mixed them quite well. And what you can see is that the granular carbon keeps that solid intact form of those particles, but SourceStop is designed to break apart as you mix it into soils and evenly coat your mixture. So you deliver something that looks like a granular carbon, but then it mixes into soils like a powdered carbon with colloidal carbon. This really enhances your distribution while avoiding those handling problems, and you can mix it in quickly and easily. Again, Steve will talk more about some of the needs from the field and how that might look. And the objective, again, is that you want to be able to deliver something to a site with minimal handling issues and get good, even distribution. And so that's what you can get with something like SourceStop solids. And so the objective, again, is that we want to immobilize our PFAS where they are and minimize that discharge from our soils or minimize what's in our saturated zone already in a source zone and moving down gradient, and help with plume management is the goal when you're doing source zone treatment like this. So I'll walk through some laboratory testing that I hope really the point is to highlight the benefits of a smaller particle carbon, the reason why good distribution of these amendments matters. Once you've placed them in the field, what does it actually look like in terms of immobilizing or intercepting PFAS that are moving around? And so this first laboratory demonstration is meant to show that for granular carbon versus SourceStop solids that have been mixed into this column here, again, this is granular carbon at 3% by weight, and then SourceStop solids at 3% by weight. Both were mixed in well. And then what we're going to do is we flowed through these columns a dye. So it's an orange colored dye. And what you're hoping to do is that as the orange colored dye gets fed in from the top of the column, ideally you're able to capture all of that dye and have it so that it doesn't elute from the bottom of the column. But what you'll see if we play this along is that, again, both columns receive the same influent. It's an orange colored dye. You'll see that for the granulated carbon, we didn't get good even mixing, kind of like what we saw in the beaker, because your particles stay intact. And so some of the fluid as it's passing through the column bypasses the sorbents that we've placed. And so you get some of the dye in the case of the granular carbon column that makes it through. Whereas if you have nice even coating with SourceStop solids, which again is a mix of powdered carbon and colloidal carbon, you get full capture. You're just able to run into, if you're a dye molecule, or think PFAS would do the same, you'd run into your sorbent with more frequency. And so you wouldn't have this bypass that you see with a larger particle. Taking it one size fraction smaller, we'll look at the differences between powdered activated carbon alone and something like SourceStop and another lab demonstration. And so we had 3 different conditions that we'll look at. So just a control where we don't use any sorbent at all. And then we'll have one condition where we have powdered activated carbon that we put down at 10 grams. And then SourceStop, in this case, it was the liquid form of SourceStop. And we applied it so that we had the same carbon loading in both of our treated samples. And what we're going to look for is that as we simulate intense precipitation, what makes it out the bottom of these reservoirs here. And so we've got our AFFF impacted soils on top, and then a clean soil beneath. And we're going to collect the water underneath it and see what's the total mass discharge under these very heavy rainfall conditions that we get. And by heavy rainfall, we really fill the pore zones. And so you'll notice that with the control, you get essentially full removal for most of your PFAS, save PFOS, which is a little bit more strongly held onto, so you don't get full removal or full discharge even after 100 inches of simulated rain. And the reason you get such substantial removal in this case versus what we talked about in the very beginning, where you get very little or slow discharge, is that we're nearly fully filling our pore space for this lab test. And so this is almost, you can think of it as worst case scenario in terms of a precipitation event. So this is what the control looks like. And then if we compare when we have pack treated versus SourceStop treated soils, so for the pack treated, you can see we've drastically reduced the leachability for both, but there's still this big difference between if we just use powder activated carbon versus a colloidal activated carbon in the form of SourceStop. And part of this is the evenness with you can get distribution with SourceStop versus powdered carbon. But we also think there's some kinetics involved here too. So you do get some leachability over time in this demo, but again, it's a fraction of what we got in the case of an untreated soil, and then even more so, another essentially order of magnitude reduction going from a powdered activated carbon in this demo to SourceStop. And so this last couple of figures just highlights that point, is that in our control, our accumulated leaching of PFAS is pretty much 100%. And then in the case of pack treated versus SourceStop treated, they're both, in the grand scheme of things, large reductions in what you get leaching out. And there's another big difference again between SourceStop treated soils and pack treated soils. So this just to highlight the difference between different size fractions of sorbent, why distribution matters and why that small particle size matters for effectively reducing leachability and discharge from your treated soils to the groundwater. And so with that, I will hand things over to Steve, who will finish it out for us.
Yeah, thank you, Paul, for kind of setting this up Appreciate everybody's time today. As many of you know, PFAS it's a widespread global problem, right? It's a major issue that we're all going to be contending with in some capacity, and it's really going to require an adaptable approach to address. As Paul has discussed, in developing this product line, we really focused on the individual treatment zones and what is happening in each of those zones. And of course, we wanted a product technology that provided that adaptability, given we're likely to see numerous scenarios in dealing with these PFAS impacts. And SourceStop, it provides a realistic and affordable and sustainable solution to this problem. The solid and liquid format of SourceStop, it's going to provide that necessary adaptability and flexibility to develop customized solutions that really meet specific needs of each of these sites. So I guess with that being said, I'd like to call out maybe some very common usage scenarios that I think a lot of us are going to encounter, and how SourceStop is really going to apply in these scenarios. And again, a lot of this is building on what Paul has discussed and bringing it more into the practical sense, what it's like in the field. So for a vadose zone soil treatment scenario, SourceStop solid would be applied through in situ soil mixing approaches. This might be as simple as an excavator with the regular old bucket attached to it. Or maybe this is a little bit more complex, and that bucket is removed and maybe it's got some special rotary mixing head attachment to it. There's also scenarios where it's even more complex, right? And maybe there's soil mixing techniques such as an auger mixer that might need to be incorporated into this process. Maybe you need a larger diameter mixing head as part of it. Maybe you need something that can go deeper than just a simple excavator in a bucket, right? These auger mixers provide that opportunity to be evaluated with respect to depth considerations. Of course, we may also need to excavate soils, right? And we may need to be excavating these soils, and we may need to treat these soils ex situ, right? We may then need to place these soils that have been treated back into the excavation. There's a lot of scenarios where I see this happening. And of course, there's also the scenario where we have stockpiled material, and that stockpiled material needs to be treated ex situ, which at that point, once it's treated, we can relocate it somewhere else on the site. I know there's lots of scenarios out there where material has been excavated as part of some construction project, and lo and behold, they sample that stockpiled material. It's PFAS impacted, and guess what? It's still in a stockpile because they don't know what to do with it. SourceStop Solid provides a really good, affordable solution in dealing and mitigating the risk associated with a scenario of that sorts. Now, of course, each of these approaches, they really could be tailored specifically for the site, right? We can address the contaminant level, right? How much PFAS is in the system, and really what do we need to do from a dose standpoint. But we can also specifically look at what treatment interval do we really need to focus on, right? Is it the entire portion, or is it a portion thereof? So if you look on the left here, right now we're showing kind of a in situ standard machine doing vadose zone soil all the way down to the water table. But the reality is we may not have to treat all the way to the water table. We may only have to treat a portion of it, 90%, 75%. A lot of this is going to be dictated by the data that is provided in terms of what the soil results are. Now, there's also scenarios where the bulk of that contamination is still bound up in the first few feet of the site, right? So these vadose zone soils that are hung up, maybe it's an area that never sees any rain, right? And it's stuck up there. It's not leaching, too far into the vadose zone soils. The approach changes entirely, right? Maybe it's some sort of rototiller type approach machine that could be applied. Maybe it's a disking machine. There's lots of different equipment or techniques that could be applied in this scenario. And of course, it's the same thing with the ex situ approach, right? We have to evaluate all of these based on really how far down do we want to go, and does it make sense to go all the way down? Now, in each of these scenarios, right, the goal is to apply a prescribed dose of SourceStop solid and thoroughly mix it into those impacted soils, right? We are wanting to achieve a homogeneous consistency with this mix. And the purpose of this is because we're immobilizing PFAS contamination, we're reducing that leachability, and ultimately we're protecting groundwater. We're protecting groundwater at very, very low levels. So that consistency becomes very, very important as part of this process. And really what you see on the left-hand side here in this picture is just it's a standard excavator, and we're just getting started. We've put in our amendment and we're starting to mix this in. The photograph here on the right, this is my hand. I'm holding up some soils here that really, this is what we're targeting. We're looking for that good homogeneous consistency when we are done mixing before we decide that, hey, we're moving on. Now, when physically handling SourceStop solids, right? When you broadcast this in and you distribute it into the soils, and this is really what you're doing, you're using most likely very large pieces of equipment, and you're physically handling this in a manner that warrants distribution of this material into the soils. You're broadcasting it in there, but that solid format of SourceStop solid, it's been engineered, right, to avoid any of those handling issues, right? This prevents safety issues such as dust inhalation, right? Nuisance dust or fugitive dust that, going off a site, maybe the neighboring properties, there's some sensitive receptor there, right? Maybe even it's just a simple activity adjacent to the work area. But it minimizes the need for dust suppression equipment specifically to address this nature. Now, when SourceStop solid, when these particles encounter water, right, moisture in the soils, or maybe we're hydrating the soils to begin with, when they encounter water, they are going to disintegrate and release that colloidal activated carbon, right? And in this point, it's going to enhance the distribution. Here's a really good video. It's just a small little sample of the SourceStop solids, and we're pouring it into the beaker, and without any mixing, lo and behold, these solids, they disintegrate and it releases that colloidal activated carbon. Now, again, it enhances the distribution, right? You get the benefits of the kinetics, and it's really improving that distribution through contact and coating of the soil particles in that very thin layer of activated carbon, 1 to 2 micron size in particles, right? Now, this allows that material to penetrate any low permeability soils that haven't already been influenced by that physical mixing process, right? Again, it's kind of a two-step approach. You've got the physical mixing, and then you take advantage of the SourceStop solids disintegrating, releasing that colloidal activated carbon. And of course, this enhanced distribution, it's going to improve the contact that's needed, and it's also going to probably reduce the mixing time required as part of this overall process. So further, these scenarios really could be combined to incorporate both parts or various parts of the source treatment. You may want to focus in on a capillary fringe injection, really just to target that high concentration mass at that air-water interface. And here, SourceStop liquid would be applied, and in this case, we'd probably apply it through a direct push injection approach, likely under low pressure. And the focus here is we're immobilizing the PFAS in the soils, as well as immobilizing any of that dissolved phase contamination that's hanging out at that interval. And of course, this approach, it can be advanced further into the groundwater, right? Or we simply could just start at the bottom and work our way back up in order to absorb that contamination that's already gotten into the groundwater, and which at this point, this is what you're doing, is you're cutting the head of the plume off, right? When you target the source area groundwater, you're cutting the head of the plume off, which is significant in terms of long-term longevity of a treatment of this nature. And of course, this may include groundwater injections and like a physical capping scenario, right? You're immobilizing the dissolved phase mass, and if you're doing a capping, you're going to limit rain infiltration. You're going to prevent any of that rain to percolate through those soils and carry down the PFAS that's hanging up on those soils. Or it might be a combination of a capillary fringe injection, groundwater injection to target the dissolved phase, as well as an ex situ or maybe even an in situ soil mixing approach where you're you're focused in on reducing the leachability of the PFAS impacts on those Vados soils. So SourceStop, it provides options, it provides flexibilities in the scenarios of addressing source contamination regarding PFAS. So beta testing, right? This is kind of where we transition from everything that we've been talking about, discussing, and really kind of theorizing to testing in the field and really putting it all to practice with real scenarios. And of course, our first beta site was a military base airport located in the Midwest. AFFF had been released onto the ground surface and impacted the site soils and really developed a large groundwater plume that happened to be migrating off site. And we went out there with the primary objectives of immobilizing PFAS impacted soils. And in this case, we were particularly focused in on those Vados zone soils. We wanted to use activated carbon to immobilize the PFAS. Those were the sorbent focus that we had. And of course, we wanted to gain field experience regarding the treatment, what it was like to implement it. What did we need to do to get distribution? How well did it distribute? How well did it handle? And of course, we had a goal, right? We wanted to treat Vados zone soils. We wanted through immobilization. We wanted to document the reduction of PFAS leachability. We had a goal of 90 to 95%, and we went out there with a game plan that really allowed us to collect samples and document that reduction in PFAS leachability. Now, the beta test, it was really focused on a small area within a much, much larger area, and it really just measured 15 feet square, and we focused in on a vertical treatment of a ground surface down to about 10 feet. And, you know, why 15 feet square? This was really selected just more on the purpose of what could we complete in a day or a day and a half, 2 days of time. This wasn't about looking at the entire contaminated area and treating that entire area. This was more about, hey, we want to get the data, we want to do a small test area, and then we want to get out of there and move on. So the work was initiated by excavating the targeted soils and temporarily stockpiling these soils right adjacent to the work area. And once we reached the excavation completion depth, a base layer of SourceStop, in this case it was SourceStop liquid, we spray applied it to evenly coat the bottom and the side walls of that excavation. And you can see by the two photos, we're really painting the walls black. We're painting the bottom black with SourceStop. And of course, we did this base layer really just to mitigate against any potential residual PFAS migrating from above. Now, once we completed that task, we then replaced those stockpiled soils back into the excavation. And this was done in lifts. This wasn't done in its entirety. We did this in lifts, and while we were doing it, we were mixing these soils, right? We were homogenizing these soils with a prescribed dose of SourceStop and powder activated carbon. These were the activated carbon sorbent materials that we intentionally went out there to use, right? And as we were doing this work, we really focused in on distribution. So the soils with each of these lifts, they were turned over multiple times, and we had good thorough mixing done before we decided to move to the next lift. And again, the goal was even distribution, right? We wanted that activated carbon, those sorbent material. We wanted to see it throughout the treatment area. We wanted to ensure a thorough and complete treatment before we moved on. And of course, the equipment that we used to do the homogenizing of the soil, the mixing of the soil, was just a standard excavator. In this case, it had a bucket, quick release bucket on it. We could take it on and off, and we could put this special attachment, this rotary mixing head attachment on it. We could swap it back and forth. And in the end, what we found is both pieces of equipment really did a phenomenal job of soil mixing and blending this material all together. And quite frankly, I think the sandy nature of the soils, the dry nature of the Vados zone soils, the excavator bucket did a great job just as much as anything. I do think a mixing head attachment of this nature more applicable, and maybe something that's got a little bit more moisture in it. Maybe it's got a little bit more fine content, things like that. So again, part of this was figuring out what equipment might be best approach to use out here and what this makes sense to do. Now, baseline samples were collected before the treatment to provide PFAS leachability data, and this was done via synthetic precipitation leaching procedures. Average total PFAS concentrations were 1,300 150 parts per trillion. You can see that right here. This is our baseline sample. This is our average right here. We did have a max total PFAS concentration in a sample of 3,835 parts per trillion. And of course, as you can see as well, the dominant PFAS strain here was PFOS, represented here in the blue, all the other PFAS compounds here in the red. Post-treatment samples, they were collected upon completing each of these lifts, right? We did the soil mixing. Once we were happy, we actually grabbed the samples right then and there. And those results indicated non-detect concentrations for each PFAS compound in all but a single sample, where we got a small little hit, small little ding of PFOS at 25.5 parts per trillion. And of course, what we're seeing here is the test results indicate PFAS concentrations in soil leachate. They were reduced by 99.4%, right? Essentially, the PFAS contamination, it's no longer migrating downward through those vadose zone soils. It's being immobilized, right? And it's not going to be discharging into the groundwater. We're now protecting groundwater in this particular area of treatment. And of course, we did collect 6 and 12-month sampling events, and results indicate, similar results to that immediately after the treatment, and really infer the expected longevity of the treatment. Now, we also performed a similar approach at another beta site in the state of Washington, where we got similar results, right? PFAS concentrations in soil leachate, they were immediately reduced to 99.5%, and 6-month sampling event also indicated the expected longevity of that treatment, and really kind of continued reduced leachability. We did collect 12-month sampling events at this site. This was done in February. However, at the time of this webinar, we still don't have those results and don't have anything to report on it, but we don't expect any significant changes impacting the success of immobilizing the PFAS impacted soils. So the effectiveness of our colloidal activated carbon technology, it's been proven on over 500 plume stop sites worldwide. This includes 51 sites treated specifically for PFAS. 5 of those have incorporated SourceStop in some way to treat PFAS source area impacts. And we've got another 145 plus PFAS opportunities or PFAS sites that are in the design phase and review phase. And this just really shows that we're actively involved in treating the PFAS impacts throughout the world. Our most recent opportunities, they've incorporated SourceStop and PRB designs, and really in this case, this is to absorb PFAS contamination and prevent migration off-site. This is a unique site in a sense that we're working in an area where they were going to do some construction activity on top of a bog, and what they were concerned with is, as they did the construction activities, it was going to compress that bog material. The bog material was laden with PFAS impacts, and they were concerned that it was going to push outside of the source area and really start to migrate off site. So we put in like a 900 linear foot barrier, essentially from surface grade down to about 6 feet. In this case, it was in the water table. We did this in the winter, everything was frozen. So kind of took advantage of the weather in this case to implement this design. We've used SourceStop liquid recently as a source area grid injection. This was done to focus in on that capillary fringe zone, really to absorb that high concentration PFAS mass at that air-water interface. And of course, we've done some ex situ soil mixing to capture PFAS contaminants bound up in the soils as part of that. This was kind of a fun one. We excavated soils out, did it all ex situ. It's what the client wanted us to do, had no problem doing it. Did it in a roll-off bin, unique mixing head attachment to get things dispersed, and working it as such to get that contact that we need. So with SourceStop and focusing in treatments on the vadose zone soils and the capillary fringe, and as well as the groundwater, as we've been discussing it, what we're doing is we're targeting the highest concentrations within the system, right? Paul earlier talked about the plume system, and when we focus in on the vadose zone, the capillary fringe, we're stopping the discharge of any contamination moving, right? And when this is done, we're allowing the plume to attenuate. And of course, if by chance you happen to have a groundwater plume that extends beyond the source area or extends beyond the property boundary or presents some sort of risk, right? Downgradient risk, a sensitive receptor or something of that nature, you can inject colloidal activated carbon in the form of plume stop at the edge of the site, right? And this would be done in a permeable reactive barrier style, and this would absorb any of those residual plume contaminants into the plume stop and really stop any further egress of that contamination. This source and plume combined approach, it really highlights our flexibility in the treatment of PFAS impacts, right? We really can treat some, or we can treat all that may need to be treated, right? We can work with you in developing the right approach, whether it be focusing on vadose zone soils or groundwater source areas. We have the options to achieve success in a lot of different scenarios. And I think just to summarize, in each of these areas, right, we're looking to do different things, likely different outcomes as well. But here, area A, it's a source vadose zone soil approach. We're focusing in on utilizing SourceStop solids, and we're stabilizing the PFAS in those soils, and we're doing it through absorption. And really, it's to reduce the leachability of those soils and prevent discharge to the groundwater. Of course, there's this area, the capillary fringe area. Right here, we would use SourceStop liquid. We're going to do this and stabilize the PFAS in the soils, reduce the leachability, and as well as retard really any of the dissolved phase mass that's at that air-water interface. And of course, if we do a source grid or a source barrier groundwater injection, we're going to use SourceStop liquid here. It's really meant to retard the PFAS that's already gotten into the dissolved phase, into the groundwater. And we're really reducing the contaminant transport rate, and this is going to allow that down gradient plume to attenuate. And of course, right, we can target that down gradient distal plume if necessary, and we can do this through a plume stop application. And here, similar to area C, you're retarding the PFAS in the dissolved phase in the groundwater. You're reducing the contaminant transport rate, but you're also preventing offsite migration, and you're really protecting those sensitive receptors that are probably driving a lot of the concern on these sites that you're working on. So to kind of summarize and the benefits of everything, when you focus in on the source and the plume treatment, right, you get this prevention of discharge from the source. It immediately stops advection from the site. And of course, it protects those down gradient receptors, and it does allow Regenesis to stand up for what it is that we really think we can do in terms of remediating these sites, and allows us to provide a warranted risk elimination program through our Plume Shield warranty. The reality is when we get to it, when you understand the source areas, when you understand PFAS and where they like to hang out, when you have a viable product like SourceStop to address it, it is actually a pretty simplistic way to go about things, right? In my opinion, it can be very easy as long as you discuss what your objectives are and what your goals are. But the product technology that we have developed here, it can be applied in a wide range of scenarios and really mitigate risk effectively and efficiently. So with that said, I'll open it up to any questions that might be out there. Thank you.
All right, thank you very much, Steve. So that does conclude the formal section of our presentation. And at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. First question is there any lab testing needed before applying the SourceStop to soils?
Yeah, I think, Paul, I can take this one if you're okay with that. But yeah, I mean, the reality is lab testing, or what we might call in the soil mixing industry, is bench testing. And I think in some capacity, it's always good to validate what it is that you're contending with, right? If you're going out to treat 20,000 cubic yards, you want to have a really good understanding of what dose rate needs to be applied or what mass loading is required to achieve those expected objectives, right? If you're shooting for 90% reduction in leachability, or maybe you have a requirement to hit 95, your mass loading is going to have an impact on that. And there's ways that we can go about in setting up a bench test, whether it be internally here at Regenesis or utilizing a third party, but you certainly want to look at that and have that option available from that standpoint.
All right, thank you, Steve. So here's a question. I know you guys went over this during the webinar, but worth repeating. What is the difference between SourceStop solid and liquid?
Sure, I'll take that one. You know, Steve, I think finished quite nicely with an illustration of where the use differences are. So really injectability is what SourceStop liquid is meant to be. So there are some opportunities for spray applications, but really liquid SourceStop is entirely colloidal activated carbon based and is meant for distribution and injection into porous media. So it's meant to put it into the capillary fringe right at the water table or in the saturated zone. And SourceStop solid is a mixture of colloidal carbon and powdered activated carbon meant to deliver in a more cost-effective way a higher sorbent loading that you need to get down to these low leachability targets that Steve was talking about. And so, you know, you can't, it's not really the right move to use entirely colloidal activated carbon when you're doing soil mixing jobs, you're treating beta zone soils. You just need a really high soil, you need a high sorbent loading. And so SourceStop solid would be the right tool for a scenario like that.
All right, thank you, Paul. So next question here regarding logistics on site. What is the packaging?
Oh yeah, great question. Didn't even bring that up throughout the discussion here. Yeah, so SourceStop liquid, that's going to be delivered to a site in 400-pound drums, as well as 2,000-pound IBC totes. And the solid component, SourceStop solid, that is going to be packaged in 1,000-pound super sacks and delivered on a pallet. Each of those super sacks would be delivered on a pallet, shrink wrapped appropriately, and obviously be dictated by the amount needed to be shipped.
All right, so let's see here. Another question here is, can SourceStop be used on other contaminants?
Yeah, that's a good question. So immobilization, soil immobilization has been around for quite some time. You know, when you're talking about using a sorbent to immobilize contaminants on soils, there are some requirements for the contaminant in order for it to be effective. You're not normally doing this on very volatile species, so chlorinated solvents, lighter hydrocarbons. You wouldn't want to use something like SourceStop solid, but for much more hydrophobic, you know, non-volatile compounds, so think pesticides and some of these legacy chlorinated pesticides, PCBs potentially, or dioxins, not dioxane, but dioxins. That's some compounds that have been successfully managed in the past by using something like activated carbon immobilization, and that would be a suitable target for something like SourceStop solid.
All right, thank you. So another question here is, do you need to reapply SourceStop?
Yeah, I'll take that one. It really comes down to what the site objectives are, and in terms of reapplication, is there incoming mass that is going to overwhelm at some point the treatment that you've put into place? And so when you're talking about soil immobilization, the goal is usually to put in enough sorbent so that your contaminant mass, whether it's PFAS or otherwise, has been met with enough sorbent that it will not really change in terms of its leachability. And so it's really at steady state. Your leaching is very, very low now, and there's nothing that's going to, quote unquote, kick off the contaminant mass. And in those situations, you would not need to do a reapplication. You've immobilized the soils for a very, very long time. If you've got incoming mass that's then overwhelming the sorbent loading that you have in place. So in a groundwater scenario, we know that barriers, for example, they have a lifetime to them depending on what gets done to anything up gradient. That may be a situation where a site might call for a reapplication. Again, it's very site specific, very situation specific though.
All right, thanks, Paul. So here's another question here. Can it be used in soils with clay?
Yeah, I think the short answer to that is yes. I think with any sort of I guess that we'll talk about on the stabilization side, soil mixing side, right? Clays can be challenging to mix up, right? Depends on the moisture content, the amount of fines that are really in it. But yeah, there's no reason why you couldn't use SourceStop solid in a more clay-based material. Distribution, contact, extremely important. The benefits of the particle size are going to be become important with SourceStop solid in combination of this type of material. But don't underestimate what it might take to mix it in, right? Physically, right? You have to have the right equipment to do it. But there's no reason why you couldn't use SourceStop solids, mixing it into a clay base. Matter of fact, you're going to get the benefits of any of those low permeability soils that are kind of hard to get to with the physical mixing process, and getting that colloidal activated carbon to penetrate into it and really disperse into those zones that really need to be touched. From an injection standpoint, so now more towards the SourceStop liquid component, as long as you can make contact and get this to disperse outward, whether it be in that cap fringe or that groundwater source area, there's really no reason why you can't inject this material into a clay materials. I would say on both fronts, yes, certainly we can do it.
All right, thank you very much, Steve. So that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again to our presenters, Dr. Paul Erickson and Steve Barnes, and thanks very much to everyone who could join us. Have a great day.